All right, thanks everyone for joining. As Shayna said, my name is Matt Scholz and I am the International Business Advisor for Automotive here at Radiant. For those who are not super familiar with who we are at Radiant Vision Systems, we specialize in developing metrology solutions that specialize in imaging technology. Radiant's been in business for the last 25 years, and over that time period, we've really revolutionized our technology and focused on a variety of different vertical markets. Everything from consumer electronics in the display industry to more emerging vertical markets like automotive, aerospace, projectors, and solid-state lighting. Our solutions range from a variety of different products, from imaging photometers and colorimeters, which we'll talk about a little bit today. Radiant is a global company, so we're actually positioned and located in Redmond, Washington. However, we do have global offices in Shenzhen, Seoul, and Shanghai with a strong global sales force and technical support team to reach all aspects of the globe. So today, we're going to talk about the SAE standard, specifically the SAE J1757-2 that's in the process of being released. This standard talks directly about head-up displays. It goes through the measurement requirements, the capabilities and requirements for developing a quality product, ensuring that safety standards and regulations are met. Radiant spent a significant amount of time over the last 18 months working with the SAE to help understand and fully develop this standard. We worked hand in hand with a variety of different OEMs, Tier 1s, Tier 2s, to understand the requirements that the industry has within the automotive market and how we as a company that specializes in metrology solutions could actually assist with providing reliable data and good process control. So the 4 points that we're going to talk about today and about enabling automation are going to be how we use an electronically controlled lens with the Radiant systems. We're going to discuss our line pairing algorithm, which is geared towards measuring modulation transfer function. We'll talk about the benefits of using a full field of view imaging solution versus, let's say, traditional spot technology. And then finally, we'll kind of wrap those three together into our final point, which is around multi-test sequencing software. This really brings everything together for an automation platform. At the end, as Shayna had suggested, we'll offer a small period of time to go over questions and answers. So I mentioned already that Radiant specializes in imaging technology, but the two fundamental types of technology that we develop are imaging colorimeters and imaging photometers. We offer 4 different types of resolutions from 2 megapixels to 29 with an 8 and 16 in between. What's nice about the solutions that Radiant develops is they're temperature cooled, they're stabilized to ensure that we have low noise floor for great measurements when we're looking at subtle defects, let's say in pixel level measurements for displays, or when we're looking at very low light levels. All of our systems have proprietary SAE matched color filters to ensure we get the best color accuracy possible. What's nice about using one of the I-series colorimeters is they have a built-in electronic neutral density filter wheel, which allows us to expand our dynamic range and ensure that we can measure much brighter sources. And this is something that we've seen is very important when we look at head-up displays, especially when we're trying to drive them at a full daytime setting. The electronic lens, which is going to be a big part of this conversation today, is a unique feature that we offer on all of our systems. The systems all come with onboard calibration data, so it's sort of a plug-and-play scenario, and our systems support USB and Ethernet control. So let's get into the meat of this presentation, which is talking about the SAE standard and the HUD measurements themselves. So as I mentioned already, Radiant has worked with the SAE committee for about the last 18 months to truly define what is necessary within the standard from a measurement standpoint, a quality standpoint, and safety standpoint. And the standard itself is based around optical metrology for automotive HUDs. Within the standard, there are a variety of different solutions that are called out for how you want to characterize a head-up display. But one of the primary solutions are imaging photometers and colorimeters, as they're easily implemented as a primary test solution for quantifying head-up displays. Inside the standard, they call out 2 primary types of tools that are necessary to truly be able to characterize and develop a head-up display. The first one is an optical meter camera or test solution. Basically something that has the ability to characterize luminance, chromaticity, uniformity, the primary components that we want to verify within a head-up display. These systems need to be photometrically calibrated, so they need to be NIST traceable, and the most obvious example is an imaging photometer. The second tool that is called out within the standard is a distance meter, and this is something that allows you to understand the geometrical distance, the direction, the angle, the distortion of the projected image that's happening out in the infinite plane. And again, one of the common examples they use is a smart camera. What's really nice about the Radiant Vision System solution is that we actually combine both of these technologies or both of these requirements into a single platform. So whether we're talking about our Y-series imaging photometer, or talking about our I-series imaging colorimeter, we have the capability to combine the optical meter component and the distance meter component within the same platform, really giving you a turnkey solution when you're looking at taking head-up display measurements. So there's a variety of different challenges that exist when we're talking about head-up displays. And one of the top 4 biggest issues that we've seen when we talk to customers and when we look at the standard itself are the following. When you look at a head-up display, you want to understand the virtual image, its location, its size, and its projection distance. You want to understand the resolution and the contrast accuracy that's being displayed within the projected image. You want to be able to quickly and efficiently project a number of different tests, look at a variety of different parameters over several different test images, and this needs to be fluid and consistent. And then finally, when we talk about moving away from the initial development in an R&D situation and go to finalized inspection or end of line, we want to be able to wrap everything that we've been developing on the R&D side and really bring it to a turnkey solution for automation. And we're going to talk about production level automated measurements and how Radiant has a turnkey solution being driven by hardware and software. So let's start talking about the electronically controlled lens. So when we look at head-up displays, this is a quick example of what it might look like in a car. So you have your driver. The driver is basically looking through the eye box, which is projecting an image out into the infinite plane. We have a specific look-down angle. We have the HUD engine itself. But as the driver, we don't actually see all that. What we do see is the projected image, so this virtual image that's sitting out in the infinite space. When we're developing a head-up display, our customers want to understand the size, the scale, and the projection distance. And this is something that can be easily understood, easily calculated by using an electronically controlled lens like the ones that we offer on the Radiant systems. So normally what happens is people want to be able to identify the projection distance. So what happens in a typical scenario is you would look through the eye box in a lab-based environment. You would have some sort of manual-based adjustment. So you would take a paravan, so some sort of white background that you would move forwards and backwards. And you usually would have 2 people trying to assist you with this. So one person's looking through the eye box and trying to judge where the physical image is sort of falling on this white background. Once that happens, you would go through and you would measure it out with a ruler or some type of tape measure. You would identify what that projection distance might look like. From there, you might tape a ruler onto the paravan itself, so then you could look through the eye box and gauge what the size and scale of the projected image might be at that specific working distance. Now, this is a very manual process and unfortunately takes quite a bit of time, and there is a lot of human error that can be induced during this process. Using an electronic lens, we can actually avoid all of that, where we can convert existing focal distance through the lens to real world units, which means not only can we determine the focal distance, we determine the virtual image size, the distance of the projected image, and what the output might look like within the software. So here actually is an example of the Radiant software within the TrueTest platform. So what you'll see is sort of our focus bar. Within our focus bar, we're trying to determine the physical distance. So our software does 2 things. So if you look on the right-hand side, you'll see that there's a focus level with a best so far bar. And at the top, you'll see we have another area highlighted, which is the focus distance. What happens is as we step through different distances within the software, we actually get direct feedback on the right-hand side within the focus level bar, and we'll see that increase. What's happening is we're actually drawing a cross section over a specific area, which is the white to the black essentially. So what we're looking to do is we're trying to see basically the 10% to 90% maximum over the white to black area, which is the contrasting area, which is giving us a direct sharp line feedback for how accurate and how in focus we might be. Once we've achieved maximum focus, we actually can read out the distance within the distance meter icon at the top. We can transfer it to the software and lock it in. At this point in time, we now have determined what our focus distance is of the projected image without having to take any sort of manual measurements or any manual setup using a paravan. Here's another example that might make it a little clearer for you to actually see. So the example on the left-hand side shows us focusing on an area where we're out of focus. And as we progress through to a different working distance, you can see we're at 3 meters as an example, the focus bar has increased. As we go to a best focus, we end up about 3.56 meters, where we've achieved maximum focus, and now we truly understand what that projection distance might be. This is a very unique way of identifying distance, and it's truly revolutionary from moving away from manual-based setups. What's nice about the electronic lens is we can quickly control different working distances. We can adjust our parameters sort of on the fly. And as I've mentioned already, we remove the human factor pretty much completely from a manual process. We also dramatically reduce time. In this slide, what we're basically showing is the lens can quickly adjust to different projection distances. So if we look at the image on the right, the first camera is basically showing a much longer projection distance at f1. However, if we wanted to adjust that distance, we could dial the electronic lens into a different focal plane and quickly get the same readout. And this is really beneficial when you're trying to understand what the different distances might be for the different HUD engines that you're working with. Now we come to an important part. So I've already discussed how we go through the process of using the electronic lens to actually determine the focal distance or the projection distance. But once we've determined what our projection distance might be in the infinite plane, we now need to understand what the size and scale might be. Radian has a unique tool that we call image scaling. This is something that is calibrated and baked into the software and hardware itself. So using the electronic lens, once we've determined basically our working distance or projection distance, we can overlay our image scaling platform. This allows us to determine the physical size and scale of the area that we're interested within the field of view. So what you can see here is we have a cell phone that's been put up. We took a measurement of it, we overlaid our grid, and you can see within the software what the size and scale is. We could draw a line through and we could get direct feedback in centimeters, inches, feet for what that area might be. And this is extremely useful when you're trying to understand the image that you're looking to characterize and what its size and scale might be. Now, when we talk about head-up displays, anyone who develops or works with head-up displays understands that the display itself is not projected in a flat plane. It actually has contouring and depth to it. So what's nice about the electronic lens is we can quickly change our f-stops to increase our depth of field based on the measurement criteria we're looking at. And this is directly actually out of the SAE standard itself. But what's very powerful about the Radiant solution is being able to calibrate a variety of different f-stops for a variety of different distances to incorporate all aspects of the HUD measurement itself. So let's talk a little bit about line pairing algorithms. So here, basically what we're looking at is the makeup of a HUD engine itself. So when we look at a HUD image, we're looking at its projection. So here we're looking at the source image that is digitally mapped to the DLP's digital micro mirror, also known as the DMD chip, and basically we're showing the projection through the windshield on the combiner out into virtual space. So this is a typical setup, but it's just to give you an idea of sort of all the pieces that are kind of coming together within the HUD combiner itself as it projects through the windshield and out into virtual space. When we're talking about preserving image clarity, this is a really important part through the development process. Improper mapping of the image with the DMD mirror array can cause modulation between contrasting areas in the image. This actually manifests as spatial frequency, so noise or blurriness, in the projection as the contrasting areas get closer. This reduces visibility, resolution, and contrast, and actually can create ghosting or distortion effects as well. So it's important to ensure that this alignment is properly managed, but it's also really important during the development to test this scenario, and it becomes even more important when you're going through production-related applications, which we'll further talk about. So modulation transfer. So the modulation, when we look at a head-up display, is basically the value that describes the resolution and contrast. Modulation transfer function, also known as MTF, determines the different levels of spatial frequencies that we see in contrasting areas. So on the right, we have a few images with different resolutions. We use these to show the improper mapping of the head-up display projection to the DMD chip array. As misalignment occurs, we see sort of a moire-like pattern where contrast between these lines becomes blurred. The resolution of the projection decreases, which shows us that we have a misalignment with the chip itself. The benefit of testing this is it allows us to determine the accuracy of the HUD system image to DMD alignment, resulting in more or less virtual image clarity. This is extremely important through all aspects of the development, but truly essential at end of line when we're trying to understand whether a product has been properly manufactured, to understand the distortion, to understand the warping, and understand the misalignment, as we had mentioned already, on the DMD chip. So what we're showing here basically is 4 different resolutions. So we have horizontal and we have vertical lines. So if we look at the top left, we're basically looking at a vertical line pair where we have about 1 pixel resolution throughout. And you can see that the contrast is quite faint. And as we move to the top right, we're seeing a much larger line graph. And this is probably 2 or 3 pixels. The bottom left one is 2 pixels with sharp contrasting scenarios. And the bottom right, we have about 5 pixel line variations per black and white line. The differences between the resolutions help us properly understand the clarity, the contrast, and resolution that not only the projection system is displaying, but also that the photometric equipment is able to characterize. So we come to this next slide, which is our line pairing algorithm. So Radiant has a nice proprietary line algorithm for measuring MTF, where we want to understand the contrasting areas within the display. So what's important about line pairing algorithm is we want to be able to calculate the modulation transfer function. So when we talk about modulation, we want to be able to calculate it for a variety of different aspects within the image software for testing different horizontal and vertical lines. The amount of modulation, as I previously mentioned, so the noise between the lines, determines the offset in the mapping of the source image to the DMD chips within the HUD systems. Once this is known, we actually can go back from an R&D perspective and apply these coefficients to apply them to the HUD system themselves for more accurate mapping of the source image to the DMD chip. In a production environment, obviously, we're not going to take the coefficients out and rejig the final product. You're actually just going to have a variety of different end user criteria for setting up pass-fail situations. So we would set pass-fail criteria based on the contrasting values that we see through different line pairs. So whether we're looking at 1 pixel variation, 2 pixel, 3 pixel, 4 pixel, 5 pixel line variations, different pass-fail scenarios would be created at end of line for characterizing the MTF and contrast. One thing you'll notice actually in this slide is you can see that there's some curvature happening within the image. And again, that's a contouring effect that happens with all head-up displays. In a situation like this, as we start to see larger contouring within an MTF projected image, we actually would want to increase our depth of field. So this initial measurement was taken with an iris f 8.0. However, what we would do after the initial measurements, we would actually increase our depth of field to maybe f11 or f16, so we could actually bring all aspects of the image into clarity. You can actually see, if you look really closely at the 9th square on the bottom right, you can see there's sort of a blurring effect, and this is because we aren't actually properly in focus at that existing depth of field. But again, going back to my earlier statement, the benefit of the electronic lens is being able to quickly adjust that stuff on the fly without having to look at any type of manual adjustments. It actually can be completely programmed for automated adjustments. So full field of view imaging. For most of you in the audience, this probably is not going to be a new topic, but it is one that's quite important. So when we look at the SAE standard itself, it calls out a variety of different measurement tools that can be used. Obviously, if you want to go through the process of using a spot-based measurement solution, you can. That's totally acceptable, as it characterizes luminance, chromaticity, CCT. You can get some pixel information, but the problem with using a spot-based measurement solution is that it's quite slow. If you're looking at the most basic of tests, let's say an ANSI 9-point for looking at uniformity of the HUD engine itself, you actually need likely 2 additional tools. You need some sort of robotic arm, or you need an XY Z stage to actually move the system from point to point. The other downfall is the fact that you're forced to take 9 separate measurements, which increases the overall measurement time, which is not beneficial when we're talking about takt times for production testing. When we look at an imaging-based solution like the Y-series or I-series imaging photometers and colorimeters from Radiant, we have the benefit of capturing the entire field of view in a single shot while also running multiple analyses simultaneously. So in this slide, basically, we're showing we could capture those 9 points as well as additional data, all within a single capture that takes 1/10 the time of what a spot-based system might be able to do. As I mentioned, the benefit of an imaging solution is being able to test multiple components sort of simultaneously. So here we show an example of how we could go through setting up a variety of different criteria and characterizing them over the same measurement. So maybe we wanted to take a single capture of a projected image and we want to look at uniformity, contrast, pixel count resolution of the information being projected, understanding the location and size of the projection image, determine whether there's any type of ghosting, distortion alignment, and potentially even modulation transfer function. Using a software platform and an imaging full field of view solution gives you that type of benefit and that flexibility. And that's just something that does not exist when you use a spot-based system. Using a spot-based system to achieve this level of information, you'd actually have to use a smart camera again. So you're forced then to invest into two types of technologies, two types of movements from either a robotic or XYZ position, and it just encumbers the entire setup. Having a single solution that incorporates all of these into either a single measurement or multiple measurements but are being driven from a fluid standpoint is a very large benefit to looking at head-up display testing from the R&D, QA to production standpoints. So here we talk about obtaining a variety of different type of data. So from the top left to the bottom right, we go through inter-character information. We're looking at resolution of projection images. We'll talk a little bit about contrast, which is obviously extremely important when we talk about head-up displays, ghosting, which is a fundamental problem, and then distortion level measurements. So we'll touch on these a little more in each one coming up. So inter-character uniformity. So I've mentioned already a spot meter requires you to take multiple measurements over multiple points. So the image on the left gives you an idea of how that would happen. You'd have a single point of interest, you'd align it 3 spots on the left, 3 spots on the right, maybe 1 spot on the circle, and 2 spots on the exclamation point. So you're forced to take 9 measurements again and move your spot meter to different locations. However, using the TrueTest software platform from Radiant, we can actually take a single image and we can quickly rectify and analyze the specific symbol that we're looking at. So what you'll see here in the image is we've actually outlined the 4 different components of the character. So the left, the right, the circle, and the exclamation mark. And what we're doing is we're giving you direct feedback on the luminance, the uniformity, the color, whether we're talking about CX, CY, U prime, V prime, CCT, of that entire outlined component. So we're giving you fundamentally more information so you can truly understand what's happening within that projection icon. Here we show you a little bit more of the same thing. So when we look at a larger field of view that might have multiple characters or symbols or icons, we can quickly run our auto POI algorithm, which goes through, identifies all the illuminated components within the scene, traces them out, sort of like an optical character recognition standpoint, and then quickly determines things like luminance, CXCY, pixel count, misalignment, image rotation, and then specific pass-fail criteria can be applied. So you'll see in the image here, basically we've set up a pass-fail criteria for luminance, for CX, for CY, specifically for a color point, which we show what that would look like in a failed position within our software, and then different components that we've looked at throughout the measurement process. So the software gives you some flexibility to not only quickly identify all the information in the projection, but also characterize it in a variety of unique and intuitive ways. Pixel resolution of symbols is quite important. So when we look at the projection of an image, we want to ensure that the user, so the driver, can properly see the projection images from a clear and absolute standpoint. You can imagine if you're driving a car and you're looking through the eye box and you're seeing a projection image and the information is not clear or sharp, it could end up being a safety issue. So during the development process, and more importantly during the end-of-line process, pixel count resolution has become a strong focus for many of the customers that we've been talking to in the automotive industry. So our software will not only identify all of the projected shapes themselves, but then we'll give you a specific pixel count, which then you can directly link back to a pass-fail scenario, ensuring that there is no proper or improper misalignment between the chip itself and the DLP projection, and that we're maximizing our resolution in the projection plane itself. Contrast. We've talked about contrast a couple times, but there are two ways within the SAE standard that contrast is being called out. Obviously, identifying modulation transfer function, which we talked about already, but the other one is understanding sequential contrast. So the typical slide that's used is a checkerboard pattern. So two checkerboard patterns are displayed, one with 5 white squares, and then a second one with 5 black squares. So the slide that we're showing right now would be of white. So you'll see the top left, top right, center, bottom left, bottom right have white illuminated boards within this 9 square checkerboard pattern. What we would do is we would actually identify those 5 components. We would take a measurement, run an analysis. Then our software would drive a secondary slide, which would put up the inverted scenario. So we'd have black where white was and white where black was, and we would run a separate analysis. Then we would run a sequential contrast algorithm, which would tell us the division between the two and give us a specific contrast ratio, which then we would directly link to a pass-fail scenario based on end user requirements. Ghosting, which is, again, as I mentioned earlier, one of the most problematic points during the development process of a head-up display, can be quite difficult to characterize. What everyone wants to understand is they want to understand basically the original image, the true virtual image, and what the ghosting aspect might be. So what our software will do is it will measure the initial image like we see here, and then we'll run an algorithm where it basically counts out the pixel sections of the original image. We'll take a second algorithm that will run over top of the ghosting aspect, which we'll define, and then we do a comparison between what the difference is in pixel count size and distance size to determine how large that ghosting aspect might be. This then allows you to take that information back, feed it through the system itself, make adjustments, or understand where the ghosting aspect might be happening or how severe the ghosting might be within the projection of the HUD unit itself. And today, there are very little ways to actually determine ghosting. There are a couple smart cameras that might exist, but using a spot-based spectroradiometer, obviously it is impossible to characterize ghosting. So having something like the I series or Y series to be able to understand the pixel count resolution, the distance, and the overlaid image through a ghosting scenario is very beneficial during the development and production process. Then finally, we come to distortion, and we'll talk about distortion a little bit more because there's two ways that we characterize it. So when we look at this slide, we're looking at a projection image that has a variety of different icons, and we can actually see that there is some distortion and warping to the image itself where it's not properly displayed on the initial plane. So for this, we would run sort of a pass-fail criteria where we would understand where the projection image was supposed to be, and then we would map it out to the incorrect orientation. So you can imagine if we look at the 84 kilometers an hour area, well, that has some twisting to the image itself where maybe that is supposed to be shifted over by several millimeters or centimeters. We could create an overlay where we identify where that projection icon is supposed to be and fail it based on the misalignment of the projection image itself. But there's also other ways that we go through characterizing ghosting and distortion, and this test pattern is directly called out in the SAE. It is the most common test pattern for identifying distortion. So there are 175 white points, and the idea, if you don't know, is you want to be able to do a few things. One, you want to be able to identify all the white points, so 1 through 175. You want to be able to mark them from top left through the bottom right so you could actually see which ones may not be present. You want to be able to fail the component based on any white point not showing up. But then you also want to understand basically the distortion offset. So you want to look at the test image distortion, you want to look at the spatial offset that's been measured between the dots, and you want to verify how it's been affected from the primary image itself. So if we look at the image on the right-hand side, you can see that we draw a variety of different lines through the entire image itself. What we're doing here is we're trying to understand where the coordinate system is from an angular perspective. We're trying to understand what the distance is from point to point and how that distance offset affects the original image that was being projected. This allows us to completely understand what type of distortion might be happening in the projection image itself, but more importantly within the HUD engine that we're looking at in this context. So then we come to multi-test sequencing. So up to this point in time, we've talked about the electronic lens, its benefit in determining projection distance, understanding scale, and size, automating aspects like different working distances, or adjusting depth of field. We've talked about the ability to quickly identify multi-test points for MTF, so modulation transfer function, characterizing distortion within the MTF measurement itself, looking at how a full field of view imager can characterize multiple test points, or how software like TrueTest can drive a display, project different slides, and characterize multiple analyses over a single image or multiple images in a more fluid way. So all of that comes together really now to be incorporated into a multi-test sequencing software. And the multi-test sequencing software that we offer at Radian is called TrueTest. Before we get into TrueTest a little more, here's an example basically of what a production level measurement might look like. So you have your imaging photometer as an example, which is positioned sort of at the look down angle. You have the HUD engine and combiner itself, which is projecting an image through maybe a tunnel or some sort of enclosure. At this point, you want to be able to set up a variety of different criteria. So you want to be able to control the HUD engine. You want to be able to flash multiple displays. You want to be able to run multiple analyses, and you want to ensure that takt times are very low as we're talking about production level testing. But although we've talked about production level testing quite a bit today, what's really beneficial is you can use the same level setup in the lab. And we're seeing more and more people sort of globally within the automotive industry looking to automate their lab scenarios. So this same setup is something that I'm seeing quite often with some of my customers who are interested really in automating their lab setup scenarios. So when it comes to enabling a fully automated testing solution, there's quite a few steps that need to be taken into consideration. You need to define your test sequence. So you need to understand what the characteristics are, whether we're talking about just the ones that are called out in the SAE standard, or if you're a tier 1 or tier 2 manufacturer and you have your own specific quality standards that you want to meet as well. So when we automate the whole process, we set up a sequencing platform. So that sequencing platform is going to allow us to look at things like uniformity, pixel defects, distortion, ghosting, modulation transfer function, contrast. But we also want to be able to set up and drive the HUD from different scenarios. So we want to project different images in a fluid, fast motion that's totally driven as a turnkey solution. We want to be able to project different test images that directly adhere to different pass-fail criteria that we're interested in. So here is a fundamental example of what that might look like. This is a direct image taken from TrueTest. So what we have on the top left is we have, let's say we want to project a white image, we want to characterize it for uniformity, but at the same time we also want to look at an ANSI brightness. Then we might have a grid-based application. So if we go back to that 175 white point inspection, we would run what we call a blob analysis grid. Then we might move on to the target reticle that you can see in this image and understand and run a points of interest scenario. Basically, I'm not going to go through all 10, but the point here is that you can set up a variety of different test sequences and test criteria that not only drive a specific projected image, but also run a specific analysis. What's great about the TrueTest platform is as we take a measurement, so let's say we captured the white measurement, well, we don't take two measurements for white to run uniformity and ANSI brightness. We take a capture for white and we simultaneously run uniformity and ANSI brightness. As those algorithms are being run, the software actually drives the HUD to project the next image and takes an image of the grid pattern. As that grid pattern is being captured, the analysis is still happening on the white layers for uniformity and ANSI brightness. We move on to the next point, which would be the target or the black or the inverse checkerboard. And the software and hardware are working simultaneously to achieve all the analysis and acquisitions of the images that we require. This dramatically reduces overall takt time and measurement time to ensure that we have a fluid, concise output of information and that we're meeting all criteria of the measurement process. Radian spent a lot of time really developing the TrueTest platform, not only obviously for head-up displays, but for all test sequences or test applications, from displays to clusters, to projection units, to AR, VR applications. It's a platform that can be used for a variety of different applications, but really is extremely robust to take into account any application that we truly feel is feasible within our platform. So If there are specific questions about TrueTest, I encourage you guys to ask them, but we also have a variety of additional information on TrueTest itself on our website that I would encourage you guys to take a look at. And at that point, that kind of brings us to our summary. So, as I mentioned before, Radian has spent a lot of time working with the SAE to help develop J1757-2. And although the standard is not officially released yet, it is truly, I believe, in its final revisions. And we've provided the SAE a ton of data to back up the points of using an electronically controlled lens to determine things like distance, size, scale, discussing our MTF measurements, and the ability to drive, the HUD unit from a fluid, concise solution, and really offer a turnkey platform. The electronic lens really makes life more simplified when we're trying to understand image location. The built-in software algorithms that I've gone over extensively already, like modulation transfer function, are unique and really allow us to understand things like visual image quality, resolution, and contrast. The benefit of an imaging solution that incorporates full field of view imaging and sort of that distance meter aspect really give you flexibility. And the multi-test sequencing software within TrueTest allows you to meet a variety of changing criteria and maximize your measurement criteria in a single concise solution. Using these systems really allows you to automate all aspects of your head-up display criteria. And again, whether we're talking about R&D, QA, or production level applications, our solutions can be fully integrated through all aspects of the product lifecycle. And at that point in time, I really appreciate everyone's time, and I'm really open to any questions that might come up.
All right, thanks, Matt. That brings us to our Q&A portion of the webinar. I understand we're a little bit past the half hour, so if those of you that can't stay, we appreciate your time, and feel free to reach out to us with any questions. For those of you that are staying in the Q&A portion, please feel free to ask questions in the question window in the GoToWebinar interface. That's usually located on the right side of your screen, and we'll start answering those questions now. So we're looking at some that are coming in.
Okay.
So I see one here for character recognition. Can you set it to recognize shapes and pass-fail based on if the shapes are correct? Do you need a golden sample to do that? And if so, how can you account for alignment errors?
Right, so that's a great question. So yes, we definitely can pass-fail based on character shapes or misalignments. That's something we've been doing for 20 years with keyboard-based applications. So whether we were talking about the initial Nokia phones or we were talking about PC keypads, we can easily characterize different icon shapes, misalignments, and broken characters. Now, having a golden sample definitely is the best way to go about it, but we do actually have a couple different ways that we can characterize it. Using the Auto POI platform, we can actually set different pass-fail criteria either from a pixel count perspective to judge misalignment, or again, as the question initially asks, we can use a golden sample. So we can create basically a thresholded region that looks at the golden sample, maps out the locations of each of the characters, its specific orientation, rotation, and pixel count, and then have that as an overlaid threshold when we're actually taking the finalized measurement. And I think there was another part to that question. How can you account for alignment errors? Alignment errors is really great, and it's something I didn't actually talk about in this presentation, but we have an algorithm that we call register active display area. So what that does is actually crops out the section based on the field of view. So you can imagine, let's say we have our image being projected, and that's the initial platform, and we register active it, and we crop down the scenario, and we look at the initial image. Well, we could run this threshold that we set up from the golden sample, but let's say the second measurement platform we put up, or the second HUD device we put up, isn't properly aligned, and maybe it's shifted by a couple centimeters to the left or right or up or down. Well, you would assume that the initial threshold that we're overlaying from the golden sample would cause a misalignment error, but actually, since we use register active display area, we crop the display or the projection image based on its new orientation, bring it to what we believe is a normalized state, and then overlay that threshold. So each measurement, regardless of its orientation or its alignment, actually ends up using the same threshold within the same coordinate system after the register active display area has been applied. So this eliminates any type of alignment errors that we might see. Okay, so let's see. Okay, yeah, that one.
Okay, so we have a question here. Would there be any advantage to using imaging spectrophotometry for HUD inspection as opposed to colorimetry?
Would there be any advantage to using imaging spectroradiometry for HUD inspection as opposed to colorimetry? You can make the argument that there would be a slight advantage if you were talking about color accuracy. As we all know, spectroradiometers out of the box obviously are the most color accurate solutions on the market. Unfortunately, they only give you a single point of interest. But using the Radiant Vision System solutions, we've actually created a variety of different patented techniques for calibrating these instruments, whether we're talking about our enhanced color calibration, our four-color calibration, or the ability for user calibrations, we can actually increase the color accuracy of our systems to meet or even exceed some spectroradiometers that are on the market. So at this point in time, I would argue that there really is no significant advantage to using a spectroradiometer or a spectrophotometer to actually look at HUD projection. Okay, so I see a question, is the draft currently available to us to look at? Unless you're an SAE member, at this point in time, the draft is not available to look at, but the finalized document should be released by the end of the year, is what I've been told. There was a revision to it that happened 2 weeks ago, but outside of that, I think everyone's kind of agreed that we're at a finalized state and it just has to work through the process within the SAE to actually become an official document now.
Okay, we have a question about how many HUD manufacturers are in North America, I'm assuming.
That's a great question. I see that question is from Gord Harris. Gord, unfortunately, I'm not sure how many HUD manufacturers exist in North America, but I can say that we are working with more than 10 different manufacturers at this point in time. How many exist within the North American field itself, I'm not entirely sure.
Okay, here's another question on what accuracy is achieved when measuring image distance. How does this compare to manual, for example, measuring tape method?
Yeah, so that's a great question. So that was something that when we first presented our solution to the SAE committee for this specific standard, there was a ton of questions. They wanted to understand, basically, are you within, a millimeter, 1 centimeter, 10 inches? So we probably took close to 200 or 250 different measurements at different distances and then measured them out manually to see what our variation was. And what we believed, or I shouldn't say believed, what the end result actually was we were within a couple centimeters at the longest distance. So everything from, the minimal focal plane out to about 5 meters, we were within sort of a centimeter or two. As we exceeded that 5-meter standpoint, so from 5 meters to 10 meters, we saw a variation from 2 to 4 centimeters as far as what that working distance would be. But within the SAE, everyone agreed that that was so insignificant at that point that it had no effect on the physical projection plane that we were looking to characterize.
Okay, here's a question on MTF. So what unit of measure is used to quantify the MTF?
Right. So as I talked about a couple times, when we're actually characterizing the modulation transfer function, we're looking at basically the frequency within the measurement itself, and then we're characterizing contrast. So again, when I showed that MTF measurement of the vertical and horizontal lines, we're characterizing the resolution and the contrast between the white and black lines. So that's the fundamental unit that's being characterized.
Okay, question here on how do we recalibrate the camera for different light source for DMD to ensure accuracy of luminance color reading?
Right. So you're not necessarily recalibrating the instrument. So when the instrument is manufactured, we calibrate it to a NIST traceable source and we deliver it to you. When you're looking at different light sources, you may want to expand your dynamic range. So as you go from a nighttime setting to sort of a mid-power setting to a daytime setting, you're going to see that the distribution of luminance is changing and potentially the color is changing as well. So if you get to a very bright source, we're actually just going to apply neutral density filters that are encumbered with, or that are built inside the I series or applied as a manual process to the Y series. The different neutral density filters are going to expand our range, so they don't require you to recalibrate the instrument, but they do allow you to read and characterize and measure much brighter light sources. From a color perspective, you're actually not looking to change anything because some of the proprietary color calibrations that we apply to our instrument take into account the varying changes over the wavelength area or the dominant wavelength of a specific color we're looking at. So the enhanced color calibration, which is a unique solution to Radiant Vision systems, takes into account varying different color changes within an image itself or within a projection itself.
Okay, so here's a question. So to find image distance for an electronic lens, do we still need to utilize a paravan? Is there any recommended projection graphics for this?
Okay, so that's a great question, and that's from Patrick McKeon. So you don't necessarily have to use a paravan, but you do need to have some sort of solid background. So whether that's a white wall, a black or gray wall, you do need to have some sort of solid color, because the idea of what's happening with the electronic lens is we're looking for sharp cutoffs within the projection image. So the original image I showed you when we were going through the focus bar was basically a white and black image. So we were focusing on the division of those two colors as the sharp cutoff point for focus. But a checkerboard pattern can be used, or anything that's projecting a symbols or characters is also fine. There is not a mandatory image that people are using for characterizing the projection distance, but anything that has a sharp cutoff, as I mentioned, checkerboard pattern, sharp contrasting areas, or even projection characters are great tools or great images to use to characterize the image distance. So I think we have time maybe for one or two more questions.
So there's a question on how large is the imager's field of view?
So the field of view is determined based on the different lenses that we offer. So Radiant Vision Systems offers a variety of specially manufactured and calibrated electronic lenses, anywhere from 12 millimeters up to 200 millimeters. Basically working with head-up displays, because everything is being operated and projected at 2 meters or greater, using a 100 or 200 millimeter lens is recommended. And that field of view then is dependent on the resolution of the camera you're looking at. So if you have a specific question about resolution or about a camera, I would encourage you to reach out and ask those questions to us directly, because it's dependent on different scenarios.
So we could take just one more question here. Okay. So last question, can your system measure the disparity parameters as well? Have you discussed such measurements while preparing the standard?
So that's a great question. One that I think I would need a little more clarity. So let me just see, Oleg. The disparity parameters, I'm not exactly sure what you're referencing here. I'm assuming you're trying to understand basically the distortion parameters within an image itself. So any type of contrasting, misalignment, or shifting within the projected image. That can be characterized in a couple different ways, as I talked about, whether we're looking at alignment or we're looking at pixel count variation. However, that is not something that has been, if I'm understanding the question correctly, that's not something that has been directly discussed within the measurement setup within the standard itself at this point in time. But maybe that is something that should be considered. Or again, if you have a specific question about that and you work in head-up displays, like, I would encourage you to reach out to me. I'd be happy to discuss that question with you a little bit further offline.
Okay, great. Thanks, Matt. I think since we're getting near to the hour here, we're going to wrap things up. I want to thank everyone for coming out. Appreciate you spending the time with us today. If you have any further questions or your questions weren't answered, please feel free to reach out to Matt. His email address is right here on the screen, so take that down and reach out to him directly. Be happy to answer questions for you. And just as a general reminder, we will be sending out slides and the recording of this webinar following the broadcast. You should see that in your inbox in the next couple days, so you could have that to review.
There were a couple questions that we didn't get a chance to answer, and I will take those questions and I will reach out to the individuals offline to answer them directly.
Yeah, we'll keep track of those, and we have all of your contact information, so we'll be able to reach out to you guys.
Thanks for your time, everyone.
Thank you, guys. Have a great day.